Okay, so welcome back to another video. So in today's video we have a double Laplace transform of the maximum function that takes into two inputs x and y. So as we know, Laplace transforms are basically integral transform that converts like a real variable, we'll say let's say t for example, a real variable t, and converts it into a complex variable s. And so we know that the standard formula for like a one-dimension Laplace transform is that it's the improper integral from 0 to infinity of e to the power negative s times t of some function f of x dx. So now what would that look like if we have a double Laplace transform? So in generality, this formula is supposed to be defined as a standard double Laplace transform of some value of some function f of x y. This is just going to be equal to the double integral, both with domains from 0 to infinity, of e to the negative, we'll call this p, and then multiply with x, and then subtract with q times y. So it's a transform from some real value xy and then converts into some complex variable p times q. Then we multiply this with our f of xy function, and then with our integration dy dx, or dx dy, whichever. Now we got this. Now the way to cover today's video is basically just plug in the max xy for our function, and then we actually did this video a couple videos ago where we computed the double integral of this maximum function. So we would have to construct how the layout of what defines that max xy would look like, which again is the same thing just from the video I did from last couple videos ago, but this time we're dealing with a different domain, so nothing's exactly changed a whole lot, so that'll be okay. And then and then basically just work out the whole ways you would calculate double integrals, and it's all set. So we have this. So now now of course defining what the maximum of xy is exactly is that it can take two inputs. One with that it would equal x, such that if x is greater than or equal to y, or it could equal, or its output is y, such that x is strictly less than y. So we would actually have two different values when we plug in our max. So this way we have that. So now if I put in the max of x and y, and so really this just means that I would have to substitute the function back in. So e negative p times x minus q times y, then max of x, y, dy, dx. Now, of course, this would mean that you can actually see the picture of this layout is that if x and y are equal to each other, then you can sort of graph this out, and it shows that it's a linear function, y equals x. So everything above that linear function means that such that if x is strictly less than y, then that the top region would equal y, and then the bottom region of that is the opposite, it would equal x, following this inequality. And of course this is actually integrating from our domain from 0 to infinity. So what this entails is that now if we just substitute the max xy, then we have two different integrals to calculate in respect, integrate in respect to y. So here we have that this is, so I put this in the brackets. So we have one that we're integrating from 0 to x, and that would fit the condition for x, the max of xy is equal to x, then multiply that with e to the negative px minus qy dy, and then we add this with our integral. This is going from x to infinity of y times e to the negative px minus qy dy, and then dx. We're going to calculate these two integrals, so we'll stick by one. So let's start off with the first integral. We're going to calculate our x times e to the negative px minus qy. Okay, so first, let's see, 0, then x x e negative px minus qy dy. Since this integration depends on y, we have an x times e to the negative px, and of course using the your rules of exponents, you can separate this by multiplicity of the e bases. Since this does not depend on y, this is basically a constant, so I can actually factor that outside. And so all we have is that we just have to integrate e to the negative qy. That's not hard to show. That you see that you can actually use or perform integration by parts. And if we work all this out, we get that. So this is just keeping the outside constant, and then in the bracket is our whatever we just integrated. So this is actually just equal to -1 divided by q. Then e to the negative qy, and then we compute our bounds from between x, well, from 0 to x. Now continuing forward, if you do all this, we have that if you plug x, then of course this is just -1 divided by q, then multiplied by e to the negative q times x. Okay, and then if you plug 0, so 0 over here, then that'll just be 1. So this is minus and then minus, so this will be a plus, and then 1 over q. Now just distributing this, our e times e to the negative px. Therefore, well, this is a positive, so I'll actually just move that to the front. This is basically commutative. So we have that this is x times e to the negative px, then divided by q. And then we subtract this with x, then times e. And then there's a negative x for both of these, so I can just factor that out. And then this is times p plus q, and then all this being divided by q. Now I could combine this into one denominator, but for the sake of simplicity, and then eventually some stuffs are going to cancel out later, so I'm just going to leave it out the way it is. All right, so now the next integral we got to calculate is the y times e to the negative p x minus qy dy. So let's actually jump into that. So now we have, so this is from x to infinity of y e negative px minus qy dy. So of course we have a e to the negative px that does not depend on this integration, so I can factor that out. So let's see, e negative px infinity. So now we have y times e to the negative qy dy. As you can see, we actually have to perform some integration by parts. So therefore, what I can do is I'll let u equals y. So we differentiate both sides. I'll get that this is du is equal to dy. And then over here, dv, I'll let that equals e to the negative qy dy. We integrate that, we get that v is just equal to -1 divided by q, and then times e to the negative q times y. Okay, now substituting this back in. So let's see, u times v. So that way I'll have, well, let me keep the e to the negative px outside first. Okay. Now from here, so we have -y then times e to the negative q times y divided by q. And of course this is being computed for our bounds from x to infinity. And then now this is v times dy, so it's minus, but I can actually factor out the negative as well, but also the -1 over q since we're integrating this in respect to y, so that's a constant. So then this will change to a plus 1 over q, and then the integral from x to infinity of e to the negative q times y dy. Now from here, just calculate this integral, so that's not that hard to show. So let's see, I'm going to keep this the way it is, so negative px. I'm not going to compute the bounds just yet, just make sure I have everything integrated first before we can continue forward. So now over here, then if we compute this integral, this will be -1 over q times e to the negative qy distributed 1 over q. This will change it to a -1 over q square of, what was it, of e to the negative q times y. And then of course divide this from x to infinity. Then if we actually calculate our bounds, then we have e to the negative px. So I compute this from x to infinity. So this way I'll get, let's see, if I plug infinity for here, so we have a negative e to the negative infinity, the whole thing just becomes 0. then you plug x. So really, then that'll become a positive since it's a minus, and then evaluate it at x. So this will be x e negative qx, then divided by q. And then we evaluate this from x to infinity. Infinity over here, this will just become 0, and you plug x. So this will just be e to the negative q times x. Well, actually, this is minus 1, so that becomes a positive 2. So this will be plus e to the negative qx, and then divided by q. Now, if I just distribute this, then since there's a negative px and qx, I can factor out a negative x, and the same thing can be said for over here as well. So this way, I have x times e to the negative x that's multiplied with p plus q. Then we divide this by q, and then we add this, and then same thing, e, then factor out the negative x, p plus q, and then divided by q. Or rather, I forgot there's supposed to be a square over here, so square. Okay, that's better. Let's actually substitute everything back in. So now, this way we have, so this is the integral 0 to infinity. Put this in parentheses, so I'll put that this is the next spot right here. So over here we substitute the red, that's for this integral over here, and this is just x e negative px divided by q. Then subtract that with x e negative x, then p plus q, then divide this by q. Then we add this with the top over here, so x e negative x, p plus q, then divided by q, and then add this with e negative x, p plus q, and then divided by q squared. Okay, and then of course dx. So notice that these two terms cancel each other out over here. So now all we're just left with is just the left of the expression and the right. So we have to, so we have x e negative px divided by q, and then that plus e to the negative x, p plus q, and then divided by q squared dx. Now the last thing we have to do is now we just got to calculate this integral. Now what we can do is I can use linearity and split this into two integrals, but not only that, there's a q in the denominator. Since it does not depend on x, I can just factor that out, treat that as a constant. So now we have that this is 1 over q, and this is the integral from 0 to infinity, x times e to the negative px dx, and then plus 1 over q squared, e to the negative x, p plus q, and then dx. And now this is basically just do the same thing again, doing with use substitution, or not use substitution, I mean integration by parts. You just let u equals x, then that means differentiate both sides, du is equal to dx, then let dv equals e to the negative px dx, and then so integrate this, we have that this is negative 1 over p e to the negative p over x, right? Now we just put the pieces together, so this way u times v, so it will be negative x times e to the negative p times x, then we divide this by p. Keep in mind that I'm just ignoring the 1 over q and 1 over q squared later. We're going to eventually later come back to it and distribute it. So we're just focusing on the integrals for now. Then we integrate this between 0 to infinity. Then this is a plus because I can just factor out the negative 1 over p. And then this is the integral 0 to infinity of e to the negative px dx. Now we do all this, then this is negative e, negative px, and then divided by p. Still keeping the same thing from this the left term. We're just taking care of the right term for just a sec. Do this again, so this is minus 1 over p squared, then e to the negative px, then from, of course, 0 to infinity. If you calculate all this out, you're going to get that this is this left side's just going to equal 0. That's pretty nice. And then over here, if you calculate this, let's see, infinity, So negative e to infinity, that's just 0, then minus, plug 0 here, that's just 1. So this will be 0 minus 1 over p squared, so plus 1 over p squared, and then just 1 over p squared. Now to calculate this integral, so now the integral 0 to infinity of e to the negative x, then p plus q dx. This is pretty simple, so this is just due to u sub. So then we have that this is just minus 1 divided by p plus q of e to the negative x, p plus q, and then from 0 to infinity. Plug infinity, the whole thing becomes 0. Plug 0, you're just going to get 1, so this will be a minus minus, so this is just equal to 1 over p plus q. Okay, and so now plugging this back in. See, we're almost done. So let's see, we have the 1 over q, then we substitute this back in for, that'll be 1 over p squared. Here, let me actually draw this so we know that this is going from here to here. Well, the whole thing, not just this, but you get the idea. Okay, then plus 1 over q squared, and then replace this integral for our evaluated answer. So it's p plus q, and then now just distribute everything back in. So this is that the final answer is supposed to be 1 divided by p squared times q, then plus 1 divided by q squared multiplied by p plus q. And so that's just equal to the double Laplace of the max of x, y, like so. All right, now there you have it. This is actually pretty neat, since I don't think double Laplace transforms don't really have a lot of discussions or talks, since it's usually the single dimension Laplace transform that everybody's like well acquainted, if anybody's taking like differential equations especially. So it's pretty neat, right? I say so. So yeah, that's pretty cool if you ask me.